Now we'll learn how to draw the Lewis structures of covalent molecules. And I've outlined a few steps to help you along in the process. When you're first starting, these are helpful. And the best way to do this is to look at an example. And a good example that I like to use is the carbon dioxide molecule, CO2. Now the first step is to count all of the valence electrons for each atom in the molecule. And we're only counting the valence electrons, and carbon has 4 valence electrons, and then oxygen has 6, but we have 2 oxygen atoms in the molecule, so make sure you multiply that by 2. So we have 12 plus 4 valence electrons. We have 16 electrons total. And one thing that I like to do is divide that by 2, and that will tell you you have 8 electron pairs in that molecule. And when all goes well in these structures, you should have all of your electrons paired and no single electrons by themselves. The next step is to decide which atom is the central atom. And usually it's the one that there is only one of, right? Like carbon in this molecule. It could also be the one that makes the most bonds. Carbon likes to make 4 bonds since it has 4 empty spots in its valence shell, right? It likes to get 4 electrons to complete its octet. Oxygen likes to make 2 bonds because it only needs 2 electrons to complete its octet. So we'll see how that goes here. So in this molecule, carbon is going to be the central atom. So we'll place that in the middle. And then oxygen is called the outer atoms. And we'll connect these by single bonds. Each single bond is 2 electrons. So those single lines representing single bonds are 2 electrons each. And one thing that we should do is count up the remaining electron pairs. So we've used 2 electron pairs, so we have 6 electron pairs left over. And the third step says place the remaining electrons as lone pairs around the outer atoms. So let's draw our structure that we've got so far. We have 6 electron pairs left to place, so we can put 3 electron pairs on each oxygen, the outer atoms. And these are called lone pairs when they are not involved in any bonding, and they're just either called non-bonding electrons or lone pairs. So we place those lone pairs around the central atom, and then the last step says complete the octets of all atoms by sharing some of those lone pairs, if necessary. In some cases, this is not always necessary. And so to complete the octet, we look at oxygen in this structure. It's got 8 electrons. So these oxygen atoms both have 8 electrons around them. And the electrons that are bonding count as belonging to the oxygen and the carbon. So these electrons that are the bonds are shared. So they belong to carbon and oxygen. So carbon only has 4 electrons around it, and it wants to complete its octet, so it needs 4 more, or 2 more pairs. And the way that we can do that is to take one of these lone pairs and share it between carbon and oxygen. And when that happens, we have 2 double bonds. So now carbon has 8 electrons. These are called double bonds. They count as 4 electrons, and they belong to carbon and oxygen. So oxygen has 8 electrons, carbon has 8 electrons, the other oxygen has 8 electrons. So the octets are full, and that's what you want to see in a complete structure. So everything has 8 electrons, and everything is satisfied. Their valence is satisfied. They've got complete octets. So that's nice. Another example we'll take a look at is with ions. So sometimes you have covalently bonded molecules that are ions, and there might be an extra step involved with that. Let's take a look at the nitrate ion. So the nitrate ion is a polyatomic ion, and the atoms are covalently bonded, but it happens to have an overall charge on the molecule. So let's take a look at how we do this. So first we'll count all the valence electrons. Right, nitrogen has 5, oxygen has 6, we have 3 oxygens in the molecule, so we need to multiply that by 3, and the negative charge means we have to add 1 more electron. So in this structure we should have 24 electrons total. So if you had a positive charge, you would subtract 1 electron. So let's divide that by 2, and now we have 12 electron pairs to place in this molecule. And to decide which one's the central atom, we decide which one makes the most bonds, and which one there's only one of is nitrogen, and nitrogen likes to make 3 bonds, oxygen likes to make 2 bonds, so we'll put nitrogen in the middle and connect the oxygens with single bonds. Okay, and so we've used up 3 electron pairs, so that means we have 9 electron pairs remaining. And we can place those around the oxygens. We can place 3 lone pairs on each oxygen atom. So 1, 2, 3, 3 for each oxygen. And so now we've used up all of the electron pairs. One thing that you'll notice, though, is that oxygen has 8 electrons for each oxygen. Nitrogen only has 6 electrons. Don't forget the negative charge on the overall molecule. And so what we do here is share one of these electron pairs, and then we'll see that everything has 8 electrons. So now nitrogen has 1 double bond to oxygen, 2 single bonds, and everything is satisfied. And one thing that we'll see in this type of structure is what is called resonance. So that double bond can actually move around, and you can get different structures. One thing that can happen is the double bond can move back and become a lone pair, and then another lone pair on a different oxygen can move down and become a double bond. So now we've got this structure. Or something else can happen. Essentially the same thing that just happened. This double bond becomes a lone pair, or one of those bonds in the double bond becomes a lone pair, and this lone pair will become the second part of that double bond. So now the double bond will be in this position. And these are called resonance structures, and they're all equivalent because that double bond can be in any of those 3 positions.